Hi, my name is Jesse Goodman. I'm a PhD student at Cornell, and today I'll talk about constructing extractors for adversarial sources by extremal hypergraphs. This is joint work with Ishan Chattopadhyay, Vipul Goyal, and Shin Lee. So I'll start by recalling what an extractor is and why you should care about them. Then I'll do the same for adversarial sources. I'll summarize some of our main theorems, and I'll give a light proof sketch of some of these, and I'll conclude with some open problems. So randomness is an extremely powerful resource. It is found to great use in designing efficient and elegant algorithms, in constructing secure cryptographic primitives, and in designing combinatorial objects with very nice properties. But unfortunately, most of these applications require uniform random bits, and nature only provides us with bits that often have unwanted correlations and biases. This motivates the study of randomness extractors, which asks, can we construct an object to purify the messy source of randomness found in nature? And so this object is exactly the extractor. We model the uniform randomness that we'd like to output as a uniform distribution over bit strings of length m. And we model the source of randomness found in nature as distributions coming from some family. So formally, an extractor is a single function, and it's defined with respect to a family of distributions and some error epsilon. And it's defined as a function such that for any distribution from that family, given as input to the extractor will output bits that look close to uniform. And here, closeness is measured by statistical distance, which you can roughly think of as L1 distance between the two distributions. And so in constructing an extractor, we like to optimize for three things. First, we'd like to make the family of distributions for which it works as expressive as possible to capture things we might find in nature. Second, we'd like its error to be as small as possible, and we'd like to output as many uniform bits as possible. And third, we need our extractor to be explicit in the sense that it should be deterministic and efficiently computable. And this is needed to unlock those applications discussed earlier. So the main question now is, what is kind of a natural and a reasonable selection for this family of distributions? Well, in order to extract any randomness at all, we need each distribution in this family to have some randomness. And typically in this field, the measure of randomness in a distribution is defined as min entropy. And so a source or a distribution over bit strings of length n is defined to have min entropy at least k if that source realizes to each value in its support with probability at most 2 to the negative k. And so you could think of such a distribution as looking something like this. And for the sake of this talk, you could think of a distribution as having min entropy k if it's uniform over some subset of the hypercube of size 2 to the k. So the question is this enough of a restriction? If we just take the family of distributions where each distribution has some min entropy guarantee, can we construct a single function that turns each one uniform? Well, a classic impossibility result says no. Even if you assume that each distribution has very high randomness content, very high min entropy, it's still impossible to construct a single function that turns each one uniform. And I won't go through the proof here, but here's a proof by picture if you'd like to pause and take a look. Okay, so it's not enough to just enforce that each distribution in the family has some min entropy guarantee. So the next most natural thing that people have studied is as follows. So instead of having each distribution being one distribution with min entropy guarantee, now we're going to take each distribution to consist of several independent sources, each with its own min entropy guarantee. This is known as the independent source model. And it turns out that we've been very successful in constructing extractors for this model. And so existentially, probabilistically, even given just two sources with logarithmic entropy, we're able to construct an extractor that outputs bits that are exponentially close to uniform. And explicitly, a recent line of work and some great breakthroughs have almost matched these parameters. We have been able to almost match these parameters. But the question here now is this actually a realistic model for randomness extraction? Does this model things we might find in nature? So in particular, we have two strong assumptions. The first strong assumption is that each source in our product distribution is guaranteed to have some min entropy. And the second strong assumption is that the collection of sources in our product distribution are all mutually independent. So let's revisit the original application and see where these might break down. So recall we wanted to harvest randomness from nature. And so given these random sources occurring in nature, we'd like to construct a single function such that turns these random sources uniform. And so if each random source is independent of the rest and is always guaranteed to output samples that have some randomness content, we can simply apply a standard independent source extractor and be guaranteed to output uniform bits. However, this is a strong assumption, and it doesn't take into account that some natural source of randomness may be unreliable and not actually output bits that contain entropy all the time. And this is known to happen with things like Zener diodes. And in this case, it's certainly not guaranteed that an independent source extractor will output uniform bits. And the situation gets even worse if some of the sources are correlated. So an independent source extractor assumes all of its sources are completely independent, and so it's certainly not guaranteed now to output uniform bits given such sources. So what we'd like to do is generalize the independent source model to kind of a more robust class so that constructing extractors for this more robust class can handle these issues and can get uniform bits even in these adversarial settings. So kind of abstracting away the application here, what we've done is we've considered two significant kind of generalizations. We started with independent sources, and then we said, okay, maybe some of the sources actually don't have any entropy, and we call these bad sources. And then we generalized it further by saying, perhaps the bad sources actually depend on the good sources in some way. And so as a bonus, we get some bonus applications from this abstraction. And so one, for example, is perhaps we can use extractors for this more general model to generate uniform bits, even given just many samples from one natural source. Kind of another bonus application is extractors for these so-called adversarial sources will be able to generate common random strings, which are very useful for cryptographic primitives. And we'll be able to do this even in the presence of synchronous and asynchronous adversaries. So that's the goal. We'd like to construct extractors for adversarial sources. In order to do this, we'll also need to impose some bound on how the bad sources depend on the good sources, which we'll see right now. And so formally, an adversarial source is defined as follows. So you can think of the big parameters as relating to global properties and the little parameters relating to local properties. And so an NK adversarial source of locality V consists of big N sources, each over bit strings of length little n, and you're guaranteed that at least big K of them are good in the sense that these are all mutually independent and each one is guaranteed to have min entropy at least little k. But the rest of the sources may be bad and have no entropy at all, and furthermore, they can depend on up to D of the good sources. And so we like to construct extractors for this model. So it's worth noting that we kind of constructed this setting to generalize independent sources, but this adversarial source setting also generalizes some classical settings like bit fixing sources and symbol fixing sources. And the zero locality version of adversarial sources is quite related to total entropy sources and small space sources. And our extractors for adversarial sources will end up improving the extractors for these settings. And finally, recently other researchers have considered other kind of semi-independent dependent models in which to study randomness extraction. But it turns out these models are incomparable to ours. So again, in summary, we'd like to construct a single function that turns any adversarial source into a distribution that looks close to uniform. So these are exactly what our results are. And so we construct explicit extractors for adversarial sources, and our extractors output many bits that are exponentially close to uniform. And the things we like to optimize are the number of good sources. We like that to be as small as possible. The entropy of the good sources, we want that to be as small as possible. The locality, we'd like that to be very large. That is how the bad sources depend on good sources. How many good sources can each bad source depend on? And then we have some sort of small restriction that we occasionally will introduce in order to really optimize these previous parameters. So even though we introduced the class of adversarial sources, it turns out that previous results for other models do in fact give extractors for adversarial sources. And so in 2016, Chattopadhyay and Lee constructed an extractor that can extract uniform bits from just two good sources hidden among an arbitrary number of bad sources. And the good sources have a pretty high entropy of 0.49 n. So in 2011, Camp et al. Showed that by increasing the number of good sources to n to the 0.99, they're able to drop the entropy requirement of the good sources to slightly sublinear. And so it would be interesting to see, can we continue this pattern of increasing the number of good sources and subsequently decreasing the entropy requirement of these good sources. We show that, in fact, even without increasing the number of good sources required, we're able to drop the entropy requirement of these good sources to just polylogarithmic in n. And then the first result that we'll explore is we can actually push the number of good sources required to even fewer than that in Camp et al. N to the 0.923 using connections to the CAPSET problem. And then using connections to C4 free graphs, we can drop it to n to the 0.75. Then eventually drop it all the way down to root n using some more technical techniques that we won't discuss in this talk. Then we show that at the expense of introducing a small restriction, we can actually drop the number of good sources required all the way down to subpolynomial in n. And this subpolynomial function is actually very small. It's effectively polylogarithmic in n. And then we show that we're able to push the locality all the way from 0 to polynomial in k and still extract the uniform bits given good sources that have just polylogarithmic entropy, but n to the 0.99 good sources. And so we won't discuss this in this talk. We'll focus on the locality 0 setting, but even in this setting, we have a strong generalization of independent sources to a model where the independent sources are hidden among bad sources. So in order to explore how we extract from these sources, we'll review the result from CL16 kind of in our framework, where we can extract the uniform bits from two good sources with pretty high entropy. So in order to do this, we'll reach into our bag of tools and we'll pull out our best low error two source extractor. And a reasonable thing to do is to go ahead and apply it to all pairs of sources in our adversarial source. And the reason why this is reasonable is because since two of the sources are good, you're guaranteed that one of these two source extractor calls will for sure output uniform bits. But the problem is we don't know which of the original sources in our adversarial sources were good. That's the whole generalization from independent sources. And so we don't know which two source extractor call will be the one outputting uniform bits. So we need to find a way to propagate the uniform bits from this activated two source extractor call all the way through to our overall extractor. So in order to do this, let's suppose for a second that all other two source extractor calls are constant. Now, this won't happen, but let's just assume it does. So in this case, let's go ahead and take all of our two source extractor calls and take the bitwise XOR of all of them. Now we'll want to argue that this overall extractor outputs bits that are close to uniform. So notice that the output of this overall extractor is simply the output of the good two source extractor call plus some constant. And furthermore, adding a constant to a random variable does not change its distance from uniform. And so as a result, our overall two source extractor call outputs uniform bits because that good two source extractor call outputs uniform bits. So we have this property G star, this nice property that says, okay, if we have a good two source extractor call that is fed only good sources and all the other two source extractor calls are constant, then our overall extractor will output uniform bits. And so we like our overall extractor, this circuit kind of construction to have this property, but of course it's not guaranteed. So the question is, how can we give it this property? The way we're going to do this is we're going to somehow condition the output of our overall extractor on some random variable, and we'll see in a second how this works. So what we'll want to do is we'll want to pick a random variable such that no matter how it is fixed, the output of our extractor conditioned on this fixing always has this nice property. And by our discussion, this means that the conditional output of our extractor will definitely be close to uniform, but we want even the non-conditional output of our extractor to be close to uniform. Well, this follows almost immediately using the somewhat standard fixing lemma, which says the distance of a random variable from uniform is bounded above by the distance of that random variable conditioned on anything else from uniform. And so as a result, if we can pick such a z such that this conditional distribution has property G star, then our overall extractor is guaranteed to output uniform bits. And so what we'd like to do is we'd like to design this random variable such that no matter how it is fixed, we have this nice property. Namely, we'd like to perform fixings such that this good two source extractor call outputs uniform bits and every other two source extractor call looks constant. So how can we do this? Well, what we're going to do is we're going to start by fixing all non-relevant sources in our adversarial source, all sources that don't feed the good two-source extractor call. This doesn't affect x1 or x3 in the conditional distribution. However, all two-source extractor calls that do not involve x1 or x3 automatically become fixed as a result. Now we're going to go ahead and fix all two-source extractor calls that involve just x1 but not x3. Therefore, it won't introduce any correlation between x1 and x3, but it might affect x1 a little bit in the sense that it might drop its entropy. Well, it turns out using a so-called entropy drop lemma, it's actually not too hard to show that this fixing pretty much actually doesn't affect the entropy of x1 at all. It just drops it by 1 bit roughly. So now we can go ahead and fix all the other two-source extractor calls that just involve x3 but not x1. No correlations introduced between x1 and x3 for the same reason as before. And again, the entropy of x3 just drops by 1 bit. And so as a result, we have our nice property G star, and our overall extractor outputs uniform bits. And so we have these kind of two motifs that popped up here that will appear in the rest of this talk. And these two kind of themes are activation and fragile correlation. And as long as we can ensure these things happen, we'll be able to ensure our overall extractor outputs uniform bits. So activation says that some sub-extractor call in our overall extractor is fed only good sources, and then it'll output uniform bits. And fragile correlation says all other sub-extractor calls can be safely fixed without ruining the uniform output of the good sub-extractor call, the good activated sub-extractor call. And in order to make sure that this happens, all we need to do is make sure that our fixings do not introduce any correlation between the sources fed into the activated extractor. And furthermore, we don't destroy their entropy by too much, which we've seen won't really be a problem. And so this immediately gives us the result from CL16, which is an explicit extractor for adversarial sources, where just 2 of them are good. And but these guys have pretty high entropy, 0.499. And so if we'd like to reduce the entropy requirement, we're going to need more sources because we're going to need more good sources because we've kind of reached the limit of what two-source extractors can achieve in the low error setting. So a natural thing to do is pull into our bag again and pull out 3-source extractor, which can handle much lower entropy inputs. So let's try the same thing as before and just apply it to all triples in our adversarial source. Well, again, we're guaranteed that one of these 3-source extractor calls will for sure be activated. Again, we won't know which one it is, so they'll be hidden. And we'll try to apply a bitwise XOR to the outputs of all 3-source extractor calls to kind of recover these uniform bits from in our overall extractor. In order to do this, we need to fix all other 3-source extractor calls like before without destroying the uniform output of the good 3-source extractor call. So let's do the same thing as before. Let's fix all non-relevant sources in our adversarial source. This doesn't affect x1, x2, or x4. And furthermore, it fixes all 3-source extractor calls that do not involve x1, x2, and x4. But now we need to fix the other 3-source extractor calls, and let's start with this one on the very left. Well, the second that we fix this, we're running into a problem because this is a joint function of x1 and x2. So it might introduce some correlation between them. If it does that, the good 3-source extractor will no longer output uniform bits. So fragile correlation fails. Our overall extractor is not guaranteed to output uniform bits. Yeah, the problem here is that we had 2 3-source extractor calls that shared 2 sources. So let's use this observation going forward and do something a little more clever. So again, we'll use 3-source extractor from Lee's paper in 2015. And now instead of just applying it to all triples in our adversarial source, we're going to apply it to triples such that no 2 3-source extractor calls are over the same 2 sources. So they don't share more than 1 source. There are many ways to do this, but let's just consider an arbitrary way. Notice that we're no longer guaranteed that some 3-source extractor call will be activated. But let's suppose that we were and see if we can ensure fragile correlation. Again, the uniform bits are hidden. So we're going to apply a bitwise XOR across everything and try to propagate the uniform bits. So we need to make all the other 3-source extractor calls look constant in order to show our overall extractor outputs uniform bits. In order to do this, we're going to switch our perspective to kind of a hypergraph perspective from the circuit perspective. And we'll do that by placing a vertex over each source. coloring it based on whether it's a good source or bad source. And we're going to draw a hyperedge around all three, any triple of sources that are used as input to some three-source extractor call. So there's a relationship between three-source extractor calls and hyperedges in this way. And our circuit will end up looking like a hypergraph, like something like this. So now let's see if we can perform our fixings in this perspective. So we can go ahead and fix all non-relevant sources that are not involved in the activated call in the middle there. This ends up fixing all three-source extractor calls, not involving X1, X2, or X4. We can go ahead and fix all three-source extractor calls that only involve X1. This might drop the entropy of X1 just by 1 bit, but it won't introduce any correlation between X1, X2, and X4. We could do the same thing to X2 and X4. And we have therefore fixed all three-source extractor calls because we know that no two three-source extractor calls share more than one source. And therefore, we know that our overall extractor will output uniform bits. So we've seen that assuming activation will occur, we're guaranteed to ensure fragile correlation and output uniform bits. The question is, how can we make sure activation occurs? So let's kind of revisit this hypergraph here. And what we have is we're guaranteed that any two hyperedges share at most one vertex. This is exactly the definition of a combinatorial object known as a partial Steiner triple system. So perhaps we can use results from this field to kind of inform how many sources we need to activate our hypergraph. So let's kind of dive into this analysis here. So if we've seen that if we have good sources on 1, 2, and 4, we have a hyperedge that's activated. If the good sources were located here, that hyperedge would be activated too. But if the good sources were located in a pattern like this, no hyperedge is covered by good sources, and so no hyperedge is activated. Furthermore, even if there are many more good sources, it's still possible no hyperedge is activated. So the question is, when can we guarantee that a hyperedge actually will be activated? And this is exactly when the good sources are guaranteed to cover some hyperedge. Well, this is exactly the definition of not being an independent set. And so we get that our hyperedge is guaranteed to be activated by good sources as long as there's one more than the independence number of good sources in our adversarial source. So what we'd like to do is construct a Steiner triple system with a small independence number. And so in 1994, Rodel and Sinajova showed that such Steiner triple systems exist, but unfortunately their result was probabilistic and we need an explicit construction. So how can we go about constructing an explicit Steiner triple system with a small independence number? Well, what we're going to do is we're going to consider some space and we're going to identify the vertices of our Steiner triple system with the points in the space. The key observation is in a vector space, any two lines intersect at most one point, and this is exactly the Steiner property. So what we can do is we can associate the hyperedges of our hypergraph with lines in some space. We need each hyperedge to have size 3 because it's a Steiner triple system. And so in order to do this, we simply make the ambient space a vector space over a field of characteristic 3. And now the question is, what does an independent set look like in this hypergraph? Well, it's exactly a set of points that cover no line in this vector space. And this has a name in additive combinatorics. It's exactly a cap set. And luckily, there have been some recent breakthroughs which have upper bounded the size of the cap set in this vector space by the size of the vector space, the 0.923. This immediately gives us an explicit Steiner triple system with a small independence number of the same order. And this immediately gives us our explicit extractor for good sources that have just polylogarithmic entropy and just n to the 0.923 good sources. So we'd like to somehow reduce the number of good sources we need. And we're going to kind of examine this framework that we've been building here. So we just show that given a hypergraph structure that looks like this, we can ensure fragile correlation. And furthermore, the activation that we need to ensure a hyperedge is covered by good sources and thereby our overall extractor outputs uniform bits. It's exactly alpha plus 1. And so by constructing an explicit Steiner triple system, we're able to achieve activation with just k equals n to the 0.923. So in order to improve this result, one idea is to simply construct an explicit Steiner triple system with a smaller independence number. This turns out to be kind of difficult, and a better idea might be to instead require less structure of this hypergraph that we need to ensure fragile correlation. If we can do this, maybe we can more easily construct a hypergraph with a small independence number. This is the idea that we'll pursue. So what if we require no structure at all, require this arbitrary structure? Turns out this is exactly the same as just requiring the hyperedges have intersection at most 2. And we know that we can activate such a hypergraph with just 3 good sources, simply by taking a hypergraph to be all triples. But as we've shown, fragile correlation is not possible in this setting. So we'd like to kind of look at some intermediate structure, which fragile correlation is still possible, but we can achieve activation more easily. It turns out one intermediate structure that works is simply taking a normal graph and turning each wedge into a hyperedge. And we're able to achieve fragile correlation in this setting by constructing a more robust 3-source extractor as our sub-extractor, and this will utilize a recent object known as a strong 2-source condenser. And as a result, we're able to show that we can reduce the activation requirement in this setting all the way to n to the 0.75. And this result uses an explicit construction of C4 free graphs with small independence number by Allon in 1986. This gives us our explicit extractor for good sources with polylogarithmic entropy, but now we just require n to the 0.75 good sources. So can we push this even further? Yes, absolutely. So instead of requiring the graph to be C4 free, it would be nice if we can throw out this restriction and just say, take the wedges of any arbitrary graph, turn them into a hyperedge, and use this to construct our extractor. But fragile correlation will be harder in this setting. However, we show that, in fact, it's actually still possible, and we show this by constructing a much more robust 3-source extractor that uses a recent object known as a 2-source non-malleable extractor. And in this setting, we're able to show that we can reduce the activation requirement all the way down to polylogarithmic in n, roughly. And this uses some recent constructions of Ramsey graphs by Lee in 2019. And this gives us our construction of our explicit extractor for good sources, again, with just polylogarithmic entropy. And now we require just a polylogarithmic number of good sources. So in conclusion, this is kind of the current state of art of explicit extractors for adversarial sources. And so it would be interesting to kind of break this root end barrier of extracting from adversarial sources in a restriction-free setting. And it would also be interesting to kind of handle higher locality, maybe k to the 0.99, and existentially, we know this is possible. In general, it would be cool to kind of explore this framework of combining even stronger extractors with weaker hypergraphs to improve our parameters all around. And finally, it would be interesting to kind of simplify our constructions just by building better explicit Steiner triple systems and C4 free graphs. And that concludes my talk. Thanks for listening, and I hope you enjoyed.